Uh, Hello, let's begin the lecture. It's 5th May. So let us recall what we were doing. So let L over K be an extension, i.e., you have two fields K and L and a ring homomorphism I between them. Then we consider L as a vector space over K and define the notion of the degree of an extension L over K as the dimension of the vector space L over K. And we had seen that the degree is multiplicative in the sense that if we have an extension MLK, then the degree of M over K is the degree of M over L times the degree of L over K. And then we define the notion of algebraicity. An element alpha in L is algebraic if it satisfies some monic polynomial. If it satisfies some polynomial f of x in k bracket x. So in particular, we recasted this definition in terms of evaluation homomorphism from k bracket x to L, where f of x is set to f of alpha. Right? And and then we say that alpha is algebraic if kernel of E alpha is not true. Otherwise, it is said to be transcendent. And we have seen that we introduce this notion of K of A, where A is a subset of L, and K of A is the field generated by A, and K. Smallest field generated by K and A. Okay. Some K and A. And then we had seen that the image of K alpha, image of A alpha, E alpha is equal to K of alpha, which is isomorphic to K bracket x or mod M alpha, where M alpha is the unique monic irreducible polynomial which alpha satisfies. Okay, so this is called the minimal polynomial of alpha over K. And then we talked about the most important theorem, namely, so alpha is algebraic over K if and only if the degree of the extension K of alpha over K is finite. If this were the case, then the degree is actually given by degree of the minimal polynomial of alpha. So using this theorem, we have seen several parallels. Namely, if L over K is an extension, arbitrary extension, and L sub A is a set of algebraic elements of L, then L sub A is a field over K. Okay. L sub A is a field over K. And then we have seen characterization of finite extensions. Namely, L over K is a finite extension if and only if L over K is algebraic and L is finitely generated over K equivalently. There exists finitely many algebraic elements in L such that L is equal to K of alpha 1 up to alpha n, where this rotation is from here. Okay. And then we have seen as a corollary from this that if M over L is algebraic and L over K is algebraic, then M over K is also algebraic. finally, we have seen that so this algebraicity has the following property. So if L over K is algebraic and if tau is a homomorphism from L to L, which is necessarily objective, then tau is on. So tau fixes K. If tau fixes K, then tau is on. So these are the various results we have seen, and then and then we proceeded towards deciding whether a given polynomial is irreducible or not. Because in order to construct an extension K of alpha, all we need to do is to pick up an irreducible polynomial in K bracket x and quotient it by quotient K bracket x by it. And then we obtain the field extension. So this is one of the simplest procedures where you can construct a field extension over K. So in order to do that, we need to know when a given polynomial is irreducible. So suppose f is the form a naught plus a1x plus a2x square plus a and x to the power of n. Okay. So we are dealing with R is a UFD. R is a UFD, and K is the field of fractions of R. But where this is coming from? Okay. Field of fractions of R. And then we suppose if P is a prime element of R, P is a prime element of R and satisfies the following properties. F is primitive, that means the GCD of the coefficients A0 up to AN is equal to 1, 2. And if P divides each and every AI, where I varies from 0 to n minus 1, but not including n, that means it divides A0, A1, A2, and so on up to AN minus 1, but not AN. 3. E square does not divide the constant term A0, then F is irreducible. So this is called Localization criterion. And based on this, we were able to see immediately that x to the power of n minus 2, or in fact x to the power of n minus p for any natural number n, and for any prime p in Z, this is irreducible in Q bracket x. Okay. And from this, we can easily see here that the degree of the extension algebraic closure of Q is infinite. Because for each polynomial, you are able to construct an extension which has a degree at least n. And therefore, A is algebraic closure, or let us say we don't know what algebraic closure is. A is a set of algebraic elements of in C considered over Q. So this is basically C sub A in this notation. Okay. And then we have seen two other criteria, namely using substitution. Substitution means by linear change of variables. So you can show that given the polynomial is reducible. So this is useful when you cannot apply Eisenstein's criterion directly. In which case you will change whether y is equal to x plus 2 or x plus or minus 1, or in general ax plus b, or no, not x plus b, x plus a for some a belonging to z. And make sure that so this will induce a homomorphism, isomorphism from K bracket x to K bracket y. So if the given polynomial f of x is irreducible here, then it is also if and only if it is irreducible over here. So this is the technique you use to conclude in the case when you cannot apply the essence criteria directly. Of course, what we use, we have to choose judiciously. And second, we have the localization principle. So given a polynomial f of x, and suppose it is primitive, that means the coefficients, it is in z bracket x and it is a primitive polynomial. And suppose if we have f bar, which is obtained as a naught bar, so given a prime p, take f modulo p, you have this. And of course, so you assume that p does not divide a n, so that the degree of f bar does not change. So that the degree of f bar is equal to degree of f. So because if you have a polynomial, if you are considering the polynomial over 2, characteristic 2, suppose you have a polynomial 2x squared plus 3x plus 2, and when you reduce it to f bar, you will get 3, you will get x plus 0. Because 3 is congruent to 1 mod 2, and 2 is congruent to 0 mod 2, and everything. So the degree of f bar is strictly less than f, strictly less than degree of f. So we don't want that to happen. So in this case, what we say is that if f bar is irreducible over zp bracket x, then f is irreducible over z. So using this, we have concluded that polynomials of the form x to the power of n plus px plus p square, which is in z bracket x, are also irreducible over z, or the equivalent by the process level. So this is what we have been doing for the last 3 classes. So let us move on and try to apply the concepts we have learned to solve some problems, some elementary problems. Problems are as follows. So this comes under applications of all the concepts we have learned. So this title is ruler and compass constructions. So you know what how compass looks like. So using compass, we'll be able to transfer certain distances from one point to another point, or you can hold on one leg and then move around this circle. That means a compass can be used to draw a circle and to transfer certain distances. And a ruler is something which is used to draw straight lines. But the important point you need to understand is that it is not a scale. That is to say, you won't be able to measure distances. All you can do with a ruler is to draw a straight line. And all you can do with a compass is to transfer distances, any given distances, but you don't know, you don't actually able to quantify the distance. And you'll be able to draw circles using the compass. So we know how to, for example, in the high school geometry, we learned how to bisect a straight line. Suppose, for example, we are given a straight line, and you are asked to bisect the straight line. That means you want to find a point on the straight line such that the distance from here is equal to the distance from to here. So that is what you need to do. So recall how you used to do that. So you hold the compass here, and then take a distance more than this, which is close to this point, and then draw an arc. Okay, and then similarly you draw an arc here, and here you draw this, and then you join these two lines. And then you use the basic postulates of Euclidean geometry to prove that this is the midpoint of the given straight line. And moreover, this line is actually perpendicular to the given straight line. So that is what we do. And also, you know how to suppose you draw a straight line. You consider this to be unit length. So this is just purely convention. It need not be equal to 1 centimeter, because as I told you, you won't be able to measure distances. But you can make conventions as you wish. And now if somebody asks you to draw a straight line of unit length, then you can extend this. And then using the compass from here to here, you measure this distance, and then you draw 2. And then you say, if you go to the left, you'll get -1. So you fix this direction, you call this positive, and you fix this direction, and then the opposite side will be negative. So in this way, you'll be able to construct any integer. Also, you can construct any rational number too. All you need to do essentially is to construct 1 over n for some n belonging to n. So if you want to construct the rational number n over n, all you need to do is to, once you construct 1 over n, so you measure the distance using the compass and then go m times of that length along this line. So that will help you, that will enable you to construct this rational number. In this way, you will be able to construct every rational number. So essentially, you need to know how to construct 1 over n, where n is a natural number. So this is my straight line, which is of unit length. And then I draw some straight line like this. Okay. And then I mark 1 here. I mean, of length n. Suppose I want 1 over 3. So I mark, so this is my, and I draw 1 straight line and mark 1. From here I mark 1 and I mark 1. Now I join this thing. And I join this thing. I can construct a parallel line to any given line. Okay. So because you can, so given this, if you take a perpendicular to this will be parallel to this. Okay, if you take perpendicular to this, using just what we did, then this will be parallel to this. Now you can draw this, and you can prove that this length is actually 1 over 3 by similarity of triangles. So in this way, so once you have 1 over n, you can construct m over n, and therefore any rational number. Also, you can construct not only rational numbers, but also irrational numbers. That's a very common thing. 1, so you have unit length, and then you draw a perpendicular unit length again. You know how to draw a perpendicular. Then this length is a square root of 2. And now if you mark using this compass, so this point will be square root of 2. So you'll be able to construct some real numbers, not every real number. For example, you won't be able to construct 5 using ruler and compass. Okay. So with this introduction, so we'll make the following definition. So we start with two distinct points, E naught, E1. And we take P naught, P1 as unit distance. This is purely convention. So these are arbitrary distinct points. And using this ruler and compass, we'll be able to construct any cube or any rational number. That means we can construct cube. So we take the P naught, P1 as the unit distance, and this is called the x-axis, and this is called the perpendicular to this would be called the y-axis. So this is my origin and this is my unit length, and note that this need not be 1 centimeter from it. So this is pure convention. Okay. So these points, so if you take any point x comma y, this has coordinate x and this has coordinate y. Okay. So from what we just seen, that we can construct any point x comma y in Q cross Q. So we say point P constructible the point P is constructible if there is a sequence of points P naught, P1 up to Pn. The final point is P. So such that the following holds. So if we have a sequence of points like this, so we start with P naught and P1, which are these points. So we fix unit length. That's how we begin. And then we construct a sequence of points. And if the end point is P, then that point is said to be constructible. So such that the following conditions hold. So let S sub j is equal to P naught, P1 to Pj, where j varies from 1 to n. So for each j, so starting from the point P2, P3, and so on, starting like this. So the point, each point here, each point Pj can be obtained as an intersection of two straight lines. Okay, this how do you get the straight lines? So these straight lines are obtained by joining two points of Sj minus 1. Suppose you want to construct, let us say P2. So you can, so you want to construct P3. So you already constructed P, you have already P naught, P1, and you have already constructed P2, for example. Then either P3 is obtained simply by joining any 2 points of P naught, P1, P1, P2, or P naught, P2. These are the 3 possible straight lines you can form using the points P naught, P1, P2. Or this is one process. Second process is, so take any 2 points in, so you have take a point in Sj minus 1, and using the length between any 2 points in Sj minus 1, you can draw a circle. So this is my first circle. And again, you take another point in Sj minus 1, and the distance between any 2 points in Sj minus 1, you can draw another circle. And if you obtain the given point as the intersection of these 2 circles, this is another procedure. Or you can, just like in the second case, you take the center as a point in Sj minus 1, radius as the distance between any 2 points in Sj minus 1, and straight line as joining any 2 points in SJ minus 1. Okay, so if this point is said to be constructed, so if the given point is obtained either as an intersection of 2 straight lines or uh, intersection of 2 straight lines. Hello? Intersection of 2 straight lines or intersection of 2 circles or intersection of a circle and a straight line. Okay. So what is the importance of these 3 processes? So these are the only 3 possible ways you can construct new points using a ruler and compass only. Okay. These are the so with the help of compass, you can draw a circle, and you can draw another circle, and you can make sure that these 2 circles intersect. Or you can, with the help of a ruler, you can draw a straight line and you get an intersection. Or you can draw 2 straight lines and you get an intersection. So these are the only possible constructions you can get using ruler and compass alone. Okay. So such a point is called constructible point. So if you are able to obtain En starting from P0 to P1, starting with P0 and P1, and then by a series of these 3 processes, if you get the final point Pn, which is our given P, then the point P is called constructible using ruler and compass. Okay. And now let us say P is my constructible point, x comma y. Then correspondingly, I consider the extension Q of x comma y. Theorem is as follows. If P is so given a constructible point, I attach a field extension. So this is the crucial idea. So based on the degree of these field extensions, I want to conclude whether P is constructible or not. So if P is my constructible point, then the degree of the extension Q of x comma y over Q is finite extension with the degree of the form 2 power s, where s is some positive integer. So if P is constructible, then it must necessarily satisfy this condition. In other words, if the given extension is not of this form, then P is not constructible, the contrapositive of this statement. So this is the format we are going to use to prove some theorems, to prove some to prove some impossibility of squaring a circle or trisecting an angle. So proof. So since P is constructible by the hypothesis, you'll be able to find a sequence of points P0, P1 up to Pn, which is my given P. It satisfies the such that each of the points Pj is obtained by the 3 processes above. Suppose Pj is equal to xj comma yj for okay, and let us define fj as the extension over Q obtained by adjoining x1, y1, x2, y2, xj, yj. Then you can easily see that fj is an extension over fj minus 1. And so, and fj is equal to fj minus 1 adjoined xj yj. Okay. Now, what we are going to show is this degree is either equal to 1 or 2. That will prove the theorem, because by the Tower law, Fn over F0 is equal to Fn over Fn minus 1 and Fn minus 1 over Fn minus 2 and so on, F2 over F1 times F1 over F0. By the multiplicative property of degrees, so the degree of this extension is Fn over F0 is this. Okay. But each of these either is equal to 1 or 2, so it must be of the form 2 to the power of s. So what is Fn? Fn is q of x1 by 1, xn by 1. Okay. Now, the important point is you want to show that q of xy is finite. So, okay. Now, my Fn consists of all these points. So, this is my q. This is of the degree 2 to the power of s for some integer s, some positive integer s. And then I want to show that q of xn comma yn, which is my constructible point here, is a subfield of this. So the degree must be is also of the form some. It is of the form 2 to the power of some other positive integer. Because this is how the degree is. So, and since 2 to the power of s is equal to 2 to the power of n times something. No, this is 2 to the power of s is equal to the product of this degree times the product of this. And therefore, this must be also of the same form. So all we need to show is that this is the case. So that means all we need to show is fj plus 1 over fj is either equal to 1 or 2. Okay, so the first process. So, you know, you have already seen that to construct a point using ruler and compass, there are only 3 possibilities. You obtain the point either as intersection of 2 straight lines or the intersection of 2 circles or the intersection of a circle and a straight line. Some additional conditions. Okay. So suppose Sj is the given set. So we have already constructed the field extension Fj. So I have my points x1, y1, x2, y2, xj, y2. So these are all the points I know. These are all the points I have already constructed using ruler and compass. And now using any 2 points, A1, B1, A2, B2, among these points, I can join a straight line. I can join these 2 points and form a straight line. Okay. So the equation joining these 2 points is given by y minus b2 is equal to b2 minus b1 over a2 minus a1 times x minus a1. So instead of making sure that we don't divide by 0, so we simply write it as a2 minus a1 times y minus b2 minus b2 minus b1 times x minus a1. So this equation is of the form lambda mu or lambda x plus mu y plus nu is equal to 0. Similarly, the equation of a circle with points with the center as one among these points x1, y1 up to xj, yj. So let us say a1, b1 is the center of the circle, and the distance and the radius is equal to the distance between 2 points a2, b2, and a3, b3. So using the compass, you can measure this distance and use that distance as the radius of the circle centered at this point. So in this case, the equation of the circle is x minus a1 whole square plus y minus b1 whole square is equal to a2 minus a3 whole square plus b2 minus b3 whole square. So once you solve this, solve this thing, and you'll have the equation of the circle of the form x square plus y square plus 2gx plus 2fy plus c is equal to 0, where g, f, and c are elements of f sub g, because they are obtained by simplifying the elements of f sub g. Now consider the first case. So we have the we can realize the point as an intersection of two straight lines. The first straight line is lambda 1 x plus mu 1 y plus mu 1 is equal to 0. Lambda 2 x plus mu 2 y plus mu 2 is equal to 0. So if you solve these equations, each of these coefficients mu I belongs to f sub g. And the equations, the point x comma y are coefficients of lambda 1, lambda I, mu I, and mu I. And therefore, the coordinates of this point x comma y also belongs to fg, because x is a fraction of lambda I, mu I, and mu I. Since fj is a field, since it is a fraction of the elements of fj, it must also belongs to fg. Similarly, y also belongs to fg. And therefore, the intersection of two straight lines won't add any new elements, and therefore the degree of extension is 1. Just recall how fj plus 1 is obtained from fj. It is simply obtained by adjoining xj plus 1, yj plus 1 to fj. But xj plus 1 and yj plus 1 are the solutions of these two equations, which are quotient of elements of fj and therefore must belong to fg. So no new elements are added to fj plus 1 if you take two straight lines with endpoints in fj and take their intersection. Case 2. So you have a straight line lambda x plus mu y plus mu is equal to 0, and you have a straight line x square plus y square plus 2gx plus 2fy plus c is equal to 0. And now supposing that lambda is non-zero, otherwise mu must be non-zero. If lambda is 0, mu must be non-zero. So both are 0, then you have a constant is equal to 0, which is absurd. So assuming without loss of generality that lambda is non-zero, so you can substitute for x an expression in y. So from this, you'll express x in terms of y, and then substitute that expression in here. So from that, what you get is you'll have a quadratic equation in y, because you have a y square. So x must be some, let us say, alpha y plus beta. Then when you substitute in here and then simplify the expressions, you'll have a quadratic equation in y. Okay, this quadratic equation may have roots in in Fj or may not have a root in Fj. If the roots are already present in Fj, so if the roots of this quadratic equation are already present in Fj, that means y is an element of Fj, and therefore x is also an element of Fj. In that case, you don't get any new extension by adding xj plus 1 and yj plus 1. So the degree is 1. Suppose the roots are not present in Fj, then what you do is, you know the formula for quadratic equation, b square minus 4ac over 2a. So this is an element of the base field. So all we need to do is to add this element, and you just add fj of square root of b square minus 4ac. And what is its degree? Its degree is equal to 2. So in the case of the intersection of a circle and a straight line, the degree of extension either increases by a factor of 2 or it remains the same. So in the case 3, so you have two equations, namely the intersection of two circles. So you have circles like this, 2g1x, 2f1y plus c1 is equal to 0, and x square plus y square plus 2g2x plus 2f2y plus c2 is equal to 0. Now subtracting these two equations, so you will see that 2 times g1 minus g2x plus 2 times f1 minus f2y plus c1 minus c2 is equal to 0. Since we have already assumed that these two circles are distinct, so one of these coefficients must be different. So we assume that the circles have different centers. So if you take a circle like this, then these two circles won't intersect at all. So we assume that so we have to ensure that the two circles intersect. So in this case, so this is of the form gx plus fy plus c is equal to 0, and you can consider this, and this case reduces to case 2. And from this, using these two equations, we'll be able to solve x and y. And depending upon whether you need to adjoin a square root or not, the new extension fj plus 1 over fj has degree either 1 or 2. So in all the cases, we have seen the degree increases either by the degree remains the same or increases by a factor of 2. And this proves the theorem. So let us see how we can use this theorem to prove that the angle pi over 3, namely 60 degrees, cannot be trisected using ruler and compass alone. So we have a 60 degrees. So using ruler and compass, you won't be able to form a 20-degree angle. Not possible. Of course, if you have a protractor, you can do that. It's not the point, but you have to use ruler and compass alone. All right. So trisecting an angle means, suppose you are able to find a point P, and if you join this, suppose you are able to trisect an angle. All you need to do is to find a point P on the given line. So this is my 20. Okay, this is not 20. So this is my, so this is my point P, and you should be able to, then you can join this point and this point to form 20 degrees. So all you need to do, construct a point P on the given straight line. Suppose it is possible. So you have a circle, and this is my 60 degrees, and you want to find 20 degrees. So suppose it were possible. So let us say alpha is equal to pi over 9. which is 60 degrees over 3, which is 20 degrees. Suppose it were possible that you are able to trisect the given angle. Then this point is cos alpha over comma sin alpha. This is a circle of radius 1, not 1, but the initial point P0, P1. This is my origin. Okay. Then what is the equation of this line? So is x cos alpha is equal to y sin alpha. So from this it follows that cos alpha comma sin alpha is constructible. If you are able to trisect the given angle, then it follows that the cos alpha comma sin alpha is constructible. Then q of cos alpha comma sin alpha over q is equal to q of cos alpha comma sin alpha over q of cos alpha times q of cos alpha over q. This can be done, right? So from this it follows, since it is constructible, this is of the form 2 to the power of s, and therefore this must be of the form 2 to the power of s, 2 to the power of s prime for some s prime less than or equal to s. Now what I'm trying to say is q of cos alpha over q has degree of the form 2 to the power of s prime. Now I show that it is impossible. So we call the definition cos 3 alpha. Cos 3 theta is equal to 4 cos cube theta minus 3 cos theta. Okay. In particular, if I take theta to be equal to alpha here, I will have cos 3 alpha, which is cos pi by 6. What is cos pi by 6 is? Is it cos pi by 6? Pi by 3, I'm sorry. So cos 3 times alpha, which is pi by 9, which is equal to 4 cos cube alpha minus 3 cos alpha. So if cos pi by 3, cos 60 is half. So you'll have 4 cos cube alpha minus 3 cos alpha minus half is equal to 0. In particular, we have 8 cos cube alpha minus 6 cos alpha minus 1 is equal to 0. In particular, you can write it as 2 cos alpha whole cube minus 3 times 2 cos alpha minus 1 is equal to 0. That is, if you take sigma to be equal to 2 cos alpha, so this equation looks like sigma cube minus 3 sigma minus 1 is equal to 0. So all you need to show is that x cube, if you show that x cube minus 3x minus 1 is irreducible over q, if this is irreducible over q, it is a monic polynomial. It is an irreducible polynomial, and therefore it must be the minimal polynomial of sigma. But if it is the minimal polynomial sigma, that means this extension is also equal to q of 2 or cos alpha. Right? So 2 is already present in q. Doesn't make any difference if you adjoin 2 or not. So this extension is equal to the degree 3, which is not of the form 2 to the power of s prime. Which is what you need to show. So you need to show that x cube minus 3x minus 1 is irreducible. How do you do that? Well, I think you just need to do the substitute x is equal to y plus 1 and see what happens. Y plus 1 whole cube minus 3 times y plus 1 minus 1, which is equal to y cube plus 1 plus 3y squared minus 3y minus 3 minus 1, which is y cube plus 3y squared minus 3. And now take p is equal to 3 and use the Einstein's criterion to conclude that this is irreducible and therefore this is also irreducible. From this, it follows that using ruler and compass alone, it is not possible to trisect an angle. it is not possible to trisect 60 degrees using ruler and compass alone. All right. Similarly, you can show that 2 to the power of 1 over 3, comma 0 is not a constructible point because the minimal polynomial of this is x cubed minus 2, which is irreducible over q by Eisenstein's criteria, if p is equal to 2. So you can easily see that this corresponds to impossibility of duplicating a cube. Using ruler and compass alone. So if you have a unit cube, whatever that is, let us call this unit cube. Is it possible to find a? Is it possible to come up with a cube of volume equal to 2 using ruler and compass alone? If this is possible, that means x to the 2 to the power of 1 over 3 is constructible. But as we can easily see that x cube minus 2 is irreducible, and the degree of the extension obtained by adjoining 2 to the power of 1 over 3 is equal to 3, which is not a power of 2. So just by using the notion of degree, we are able to decide one of the impossibility of doing some constructions. In the next class, we will see, we'll proceed with the general theory of splitting fields.